Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started.
All right, everyone. I am super excited to start this machine learning journey with you all. So without further ado, let's begin with module number one. So this is our introduction to machine learning. We are going to do this module in three parts. Basically, part one, I will talk at the very high level, what is the difference between machine learning and statistical learning? Some of you guys may have heard the terms linear regression in previous courses that you have taken, but we want to see what is the difference between basically those kind of econometric approach and the machine learning approach that we're going to cover in this course. In part two, we will be going over the definition of machine learning and say what is the difference between machine learning and programming. And then in part three, we will be covering different types of machine learning algorithm. Okay, part one, machine learning versus statistical learning, the big picture.
All right, so in this episode, I'm going to walk you through the difference between the machine learning world and the statistical learning world from the other hand. Let's begin with the big picture. So, what are we trying to do as a researcher or a practitioner? Eventually, at the end of the day, we want to solve some real world problems by answering some specific questions, right? Sometimes we need to either make an inference about a bunch of hypotheses, or sometimes we need to make simply predictions. And for those questions, for those real world problems, sometimes there's a theory, and most of the times there's absolutely no underlying theory. Let me walk you through a bunch of examples and it makes more sense. Okay, so imagine in marketing, we're interested to see what is the relationship between sales and advertisement, right? What's the relationship between sales from one hand and advertisement, R&D expenditure, seasonality, industry type, and etc. from other hand. So this is a really interesting question. Or, for example, you want to work as an economist for big name companies like Amazon, Google, Microsoft, Apple, and then basically you want to quantify the demand function, right? So you're interested to see what is the relationship between quantity demanded from one hand and price, income, technology, price of competitors, the price of substitute from the other hand, right? So this is also another type of interesting research question. And then finally, for example, you want to see what's the relationship between wage and education, age, gender, industry, job characteristic, and etc. Right? These are all really interesting research questions. Maybe for the quantity demanded ones, you have a beautiful, perfect underlying theory. But for the rest of the questions, there's not necessarily a theory. So we have to start from the data, right? Whatever the question is, we have to sort from the data. We have to and see, depending on the data, the type of the data set, we will end up working with either a machine learning model or an econometric model. So it all narrows down to the type of the data set that you're working with, and more importantly, what's your end goal? What do you want to do with that question? All right. So now let's look at a couple of more examples in more details to see what I mean by type of data sets and what's your goal as a practitioner or a researcher. All right, so let's begin with a very simple example. Imagine we want to quantify someone's wage components, right? And what are the drivers? The drivers can be some skill set and demographic variables like education, age, experience, IQ, or it can be some social and cultural profile variables like ethnicity, race, gender, or it could be simply some job characteristic variables like industry, location, working hours, and etc., right? Whatever the variables are, you need to build a model, right? If there's an underlying theory between wage and all these characteristics, then you can leverage from the theory and start making a model from the theory. But if in this example, when there is no underlying theory between wage and all these characteristics, at least as of today, then you should start by making some assumption, right? So you can say, okay, let's assume that there is a linear functional form between wage and all these characteristics, right? Then we can summarize the relationship like this. We can say that, okay, wage is a function of education, age, experience, IQ, and etc. Right? And we can come up with this simple linear functional form. So the questions that you should ask yourself then is that, can you interpret this model, right? And more importantly, do you care about interpretability? So what does that mean? It means that, for example, at the end of the day, do you care what's the coefficient of education, right? Is it economically and statistically significant or not, right? If that's kind of the question that you're interested in, then you're more willing to get some inference out of predictions, right? So here it says that, okay, you're looking for some inference versus prediction. Because at the end of the day, if this coefficient turns out to be significant, then you're going to say that, okay, so it seems that education, the partial effect of education on wage is significant, holding everything else constant. So what does that imply? It implies that for you as a policymaker, maybe you're going to say that, okay, we have to dedicate this amount of budget to the state for education because the model shows that it matters, the data shows that it matters, right? And from the other hand, let's see, can you make predictions using this model, right? And again, more importantly, do you care about making predictions, right? So for example, did you collect the survey data to, at the end of the day, make some predictions for other people's wage? If that's the case, then you're caring more about predictions versus interpretability, right? Versus making inferences. So this idea of which goal is more significant, it all goes back to you as a researcher. Sometimes you want to become a storyteller, you want to act as a policymaker. So in those cases, you cannot care less about making predictions, right? So you don't care that, okay, I want to come up with a model that makes predictions for wage. I want to come up with a model that I can infer something from that. So if that's the case, so your goal is to making inference. However, on the other hand, if you want to make predictions, if you purely are using this data, this model to make some predictions for some other people's wage, then your goal is to make predictions, right? So I want you to pay attention to these two terms. So this is going to help us a lot in terms of understanding what's the difference between machine learning and econometrics. So interpretation versus prediction. All right. Okay, now let's look at a different example. This is what we call image recognition, right? So for example, you're given a bunch of pictures and you want to classify them as cats versus dog, right? Where should we start? Is there an underlying theory? How can we model this thing, right? So in this example, I want you to specifically think about this question. At the end of the day, do you really care about interpretability of the model here, right? So do you really care how does this model go from taking the picture and giving you at the end of the day, okay, is it a cat or not, right? So the output is it a cat or not? Do you really care how did that happen? And basically, can you interpret these things, right? So most probably the answer is no. And another question that I want you to think about is, what about accuracy of your prediction? The answer is absolutely yes, right? At the end of the day, you want to come up with a model that if you give it some information, it will eventually be able to tell you if it is a dog or cat, right? So for example, if you pass to the model this picture, it better tells you that, okay, the answer is dog. If you give it this picture, the answer is dog, and etc., right? This picture, the answer is cat. So you do care about predictability of this model a lot versus interpretability. So the difference between these two examples that I provided is that in the first one, wage versus education one, we cared about interpretability because we wanted to become a storyteller. We wanted to say that, okay, what's the effect of right-hand side variables on the left-hand side variables? In the second example, in this image recognition example, we could not care less about interpretability. There's nothing to interpret. At the end of the day, we want to make some predictions, right? So these two simple questions are going to help us a lot in terms of understanding what is the difference between machine learning and econometrics or statistical learning. All right. Let's see if we can summarize those previous examples in a more formal way. What is the difference between statistical learning and machine learning? I'm going to go ahead and write those examples up here again. So for the statistical learning, we were doing the wage inference, right? So we want to see what are the ingredients of the wage and how they impacted the wage. For the machine learning, we looked at the wage prediction. If you're purely interested in to see how we can predict wages, predictions, that example, and the image recognition. Okay, so in the previous examples, if you were purely interested into making predictions, we were dealing with machine learning models. And if you wanted to make some inference, we are dealing with the statistical learning models, right? Now let's focus on the differences. So the first thing, focus on of attention, right? So in the statistical learning, we are interested in hypothesis testing and interpretability. This is a key term. We want to become a storyteller. We want to see what is the relationship between variables, right? In the machine learning world, we care about predictability, right? So what's the accuracy of the model? At the end of the day, we don't care about interpretability that much, right? It's not zero, but we don't care that much about interpretability. For the statistical learning, what are the drivers? The drivers are math, sometimes theory, and most of the times hypothesis, right? So you have an idea, you want to test that idea, you have some hypothesis. So you come up with a model and you try to see what's the relationship between variables. In machine learning, it's all about fitting the data, right? Give me some data and I'm going to tell you what's the relationship between variables. And not necessarily I'm interested in making those inferences, but I will tell you what are the predictions, right? Data size. In a statistical learning, the data can be any reasonable data set. So for example, a data set of 30 observations cross-sectional might be enough, right? However, in machine learning, it's all about big data, right? Those three V's, volume, velocity, and variety, right? So in terms of volume, we're talking about millions or sometimes 100 millions of records. Velocity, in machine learning, we're talking about real-term or near real-time data set, right? We're talking about seconds, milliseconds, etc. And when it comes to variety, so this is important, the variety of the data. Let's actually explore it in a separate row. So when it comes to the data type, in statistical learning, we are dealing with structured data, right? So the data sets that we can simply summarize it in nice columns and rows, right? So for example, we have wage, we have education, we have gender, and etc. So this is what we call flat file, right? So we can have a table. However, in machine learning, we deal with structured data, so simply like this wage data set, unstructured data, and semi-structured data. So the unstructured data, the examples of are like those images, voices, and videos, and etc., right? Text. And semi-structured data are a combination of structured and unstructured. For example, I don't know, the images on your cell phone, right? The image itself is unstructured, but the location and time of that photo that you've taken is going to be the structured part. So it's going to be a combination of the two. Okay, so this is very, very important because remember, guys, if your data is unstructured or semi-structured, you can simply not use the statistical learning models. You cannot use the econometrics model. You have to use machine learning models. So this is a big deal. Why? Because as of today, more than 80% of the data out there is going to be unstructured, and only 20% or even less than that is going to be structured. So this means that for more than 80% of the real questions out there, you cannot, right? Guys, remember, you cannot use a statistical learning, you cannot use econometrics, and you have to use machine learning, right? Then the next feature that we're going to explore is dimension or scalability, right? So for statistical learning, we're dealing with mostly low dimensional data because we want to keep the model simple. We want to keep it interpretable. Remember, it's all about interpretability. If I make the model more flexible, if I increase the dimension of the data to hundreds, 200s, 300s, or thousands, then it's not easy to interpret things, right? It's not easy to hypothetically hold everything else constant and see what's the net effect of one variable on the other ones, right? So basically in econometrics, in statistical learning world, we try to keep the dimension of the data very low. However, on the other hand, in machine learning, it's all about predictions, right? Give me as many predicting factors as possible. So we are dealing with high dimensional data, and sometimes we are talking about the dimensions of 100,000s, millions even. In neural networks, we're dealing with millions of dimensions, right? Okay, then the next one is model choice. So in statistical learning, we are interested in parameter significance and mostly in sample goodness of fit, right? Because remember, this is at the end of the day, you want to make inference using one data set. You're not trying to make prediction, right? So you don't necessarily need to divide the data set into train and test set. Basically, using your train set, you want to see how the model is doing a good job or a bad job, right? And we are interested in parameter significance. We want to see that, for example, if the effect of education, if the parameter, that beta 1, was significant or not, statistically and economically. However, in machine learning, we are interested in to make predictions, right? So for that reason, we're going to divide the data into train set and test set, right? And at the end of the day, we want to see what's the accuracy of the data in that test set, right? And we're going to do that by something called cross-validation. We will talk about it in the next series. Then the next one is interpretability. So this is a big deal. Right? This is a big one. This is a big distinguishing factor between statistical learning and machine learning. Remember, in statistical learning, the interpretability is high because the model is designed to perform that way. And in machine learning, the interpretability is low because, again, it's designed to be that way. You know, you make the model so flexible in order to capture, in order to make better predictions, but it comes at a cost. The cost is that your model is less interpretable. And then finally, let's look at the strength point of each of these models. So for statistical learning model, the model hopefully understand the causal relationship and behavior. And I say hopefully because, you know, correlation does not necessarily mean causation. So we have to make a bunch of assumptions. And if all those assumptions are valid, then we can say, okay, now we can think of it as causality versus correlation. And the strength point of the machine learning model is just its prediction, right? Because again, in the machine learning world, we are more interested in making predictions. It's all about nowcasting, and today, more recently, we forecasting and nowcasting. So nowcasting basically means that just use the real data, right? Real term data. All right.
Let me one more time highlight the limitation of econometrics or structured machine learning, because we know that machine learning can handle unstructured data, but it's not necessarily the best model, right? So we know that this econometric and machine learning can only handle structured data, and structured data is tabular data, right? But what is our real world? You know, the real world is mostly this, unstructured data. You know, more than 80% of the data out there is unstructured, and only 20% of the data is structured, right? So we have to go beyond econometric and machine learning. And actually in this course, I'm going to talk about almost all of these things that you're seeing in the picture. Now I will talk about object detection. So here's an example of real-time object detection. We're going to look into some models, RCNN models and YOLO models. We talk about language translation models. We look at, you know, image recognition models. We talk about self-driving cars using reinforcement learning. And this is some generative models that are generating some photos, for example. So I can say, okay, draw an astronaut riding a horse on the space. So these are generative models that we're going to talk about these things. By the way, the company behind this thing is OpenAI, and this is using DALL-E. We're going to talk about these technologies in the course later on. Okay, so yeah, that's why we have to learn deep learning, right? Because in our real world, most of the data is unstructured. Okay. Let's quickly look at the more complex example. I want to highlight that you have to, you know, as a researcher, you have to see what is the question that you have in hand, right? You don't need to necessarily always use econometric or always use machine learning or always use deep learning. You can mix them, right? If your goal is purely prediction, most probably, it's not guaranteed. The deep learning model is going to do a better job if the data set is unstructured. If the data set is structured, again, the boosting models like XGBoost, LightGB, and CatBoost, these are still the winning models out there, right? So when the data set is structured. So you have to look at the data and the structure of the data and then make up your mind, right? So here, for example, one of the $1 million questions out there is a stock price prediction, right? So imagine this is a data, and let's say we are dealing with this kind of variables, right? What are the classical drivers of a stock price? Now, company's fundamental, balance sheet, income statement, cash flow statement, and etc. We can look at the competitors, look at the multiples of the competitors. I'm not trying to get into the details. So, for example, what is PE, what is price over sales, and etc. So, but just imagine there are some features that I can look at those ratios between different companies, right? And if one company is overperforming and underperforming compared to the industry, I can buy or sell that company, right? And we can use technical analysis for stock price predictions, and we can look at some seasonality data, right? So this data, this is structured. So when this data set is structured, now I can use, if this is the only data set that I have, I can use econometric, I can use machine learning, I can use deep learning, okay? Because in a stock price prediction, we are mostly interested in the prediction part, so maybe econometric is out of the scene. We have to focus on machine learning and deep learning. If this is the data set, based on my experience, most of the time machine learning is gonna outperform than the deep learning, because we don't need a super complex model, and we just need a model that can handle these structured features in a maybe hierarchical fashion, right? Deep learning also can do that, but again, in practice, the boosting models or machine learning models are so powerful, they can handle this model better. But what if this data better? What if I want to add more information, right? What is that more information? Let's say market sentiment. This is a big deal, in today's world. For example, looking at Twitter, what's going on in Twitter is a big deal, right? So what if I want to track what's going on in the news, look at the Twitter, bloggers' opinion, conference calls, and et cetera, right? So I want to have a model that can listen to the conference calls and look at the sentiments and trade on that, right? So another example is, for example, I want to extract some information about satellite images from a parking lot, right? I don't want to wait for a quarter that the company report its inventory or sales. I just want to look at these satellite images real time and extract some information. If that's the case, then you're dealing with unstructured data, and the answer is going to be deep learning. Okay. So I hope that with this more complex example, you realize that what are available to you as a researcher, and then when should you pick econometric, machine learning, or deep learning. Okay, then why should you learn it? The answer is so simple, because deep learning is everywhere. Just look at these photos. This is our life, right? We are dealing with these things on a regular basis, right? So image recognition, we use it for healthcare, for increasing the productivity of a field, the self-driving cars, weather forecasts, search engines, and now today ChatGPT. Hopefully you're familiar with ChatGPT. I'm going to talk about the language model behind the ChatGPT in this course as well. And yeah, I think the answer is recommendation systems and et cetera, et cetera. The answer is so simple. Deep learning is everywhere, so it's a big deal. And if you're interested in this field, you should learn it. And better career opportunities. So I think it goes without saying that if you have the knowledge of the deep learning models, you have better career opportunity. It goes without saying. And what I love most is knowing these kind of stuff. It enables you to hedge yourself against the next recession, right? Because if you're econ students, finance students, marketing students, no matter what, right? At least at some point there's going to be recession in one industry. But if you know deep learning or machine learning, it really doesn't matter what industry you work in. You can be an economist or financial, I don't know, the PhD, whatever, and at the same time you can apply your knowledge from deep learning to image recognition. Okay, you can work in a team and do some diagnosis for radiologies, right? So you can become a radiologist diagnosis. So this is what I love about learning these things, these tools, machine learning and deep learning, because it enables you to work in any kind of industry. All right, that was part one. Now in this part two, let's go over the definition of machine learning and see what is the difference between machine learning and programming.
Okay, so what is machine learning? Machine learning, as we talked about it in the previous modules, is a subset of AI that enables computer to learn from the data. Okay, so this is different from the traditional or classical programming in a sense that, look at this one. This is classical programming. In classical programming, the inputs are some data and some rules. So for example, you have been given x and some rules. So let me show it with f of x, right? So this f of x can be anything. Let's keep it very simple. It's equal to x plus 3. So I know the x, I know the rule, and then the computer is going to do the math and it's going to calculate the output, right? So for example, and this output I can label it as y. For example, if x is equal to 3, or let me use a different number, if x is equal to number 6, then the output is going to be 6 plus 3, which is equal to 9, right? So this is classical programming. There is no uncertainty. The inputs are given, the rules are given, the computer is going to do the math and give you the output, right? However, in machine learning, the story is different. You have been given some inputs. The input can be X's and answers, right? So, the, in depending on the type of machine learning, sometimes you will be given the answer, sometimes you won't. This is the difference between supervised versus unsupervised. But let's keep things simple. So imagine you have the X's, you have the Y's, and the goal of machine learning is to learn from the data, right? So this is the goal, to learn from the data. What are the rules? What were the relationship? What was the underlying pattern between X and Y? So that's the goal. The goal in machine learning is to estimate this f of x. Let's show it with f hat of x, right? So this is the pattern. This is what we're looking for in machine learning. Okay, so as we said, so this means that the machine learning system is trained with bunch of rules and algorithms. So it is trained rather than being explicitly programmed. So whenever we say that machine learning is a system that's not explicitly programmed by human, this is what we mean. However, this does not mean that it's not human involved. We, the humans, are the ones who are going to set the scene, who are going to set the rules or algorithms. Okay. Now, we know that machine learning involves in automated detection of these patterns in the data and apply those patterns to make some predictions, right, on the unseen data. So the optimal goal in machine learning is to maximize the performance of the model on the unseen data. So it's all about generalization. How good your model is in terms of generalizing of predictions on something that the model has never seen before. That's the optimal goal in machine learning.
All right, so you may have seen something like this, that deep learning is a subset of machine learning and machine learning is a subset of AI, artificial intelligence. But let's break it down and see what do we mean by that. So I would like to start by the definition of intelligence. So intelligence is this ability to process information and make decisions based on that. Now, if this intelligence is a biological inspiration, as in humans, we call it human intelligence. But if this intelligence is engineered and done by machines, we're going to call it artificial intelligence, right? So artificial intelligence is any technique, let me use my pen, it's any technique which enables machines to mimic human behavior. So as you can guess, this is a difficult task. The theory was, actually, it's nothing new. It was around since 1950s. But the computation power was not there yet, so we had to start from somewhere. So we started back in 80s, we started with setting the scene for the computers. We said that, you know what, let's go ahead and these are the rules of the games. We set some rules, we set some designed some algorithms, and based on that, the machine was able to learn from the data. Okay, so this is what we call machine learning. So machine learning is a subset of AI that enables computers to learn from data, and the model is trained. The key term is this, train. I want you to pay attention to that. The model is trained with a set of algorithms. So we, the humans, are the one who set the rules and say that, hey, this is the algorithm, use that, apply it to the data, and then make some predictions, right? And then the next one is deep learning. So it was in 2010 that the computation power was there and the algorithm was there. And the deep learning is a subset of AI that extract patterns. So here the key term is extracting patterns from the data using neural networks, right? We're going to talk about the details of the neural networks, but the key point here is that we are not engineering some features like in machine learning. In machine learning, we the humans are going to set the rules, come up with some algorithms, and most importantly, we're going to engineer some features, right? The feature engineering is done manually. However, in deep learning, the entire goal is to extract these patterns, these features from the data automatically. So that's a main difference between deep learning and machine learning. And the thing is that once these patterns and features are extracted, we can pass this to a machine learning model, and the machine learning model can come up with some basic predictions, right? So that's why we say deep learning is a subset of machine learning, because when the data set is unstructured, we need to extract those patterns automatically, because hand engineering those patterns is difficult. And then once we're done with that part, we're going to pass it to a machine learning model, and the machine learning model is going to make the predictions. Okay, so that's the difference between AI, ML, and deep learning.
All right. In part 1 and 2, we covered the difference between machine learning and statistical learning. We also reviewed the definition of machine learning itself. Now in part 3, I'll cover different types of machine learning algorithms, namely supervised, unsupervised, and reinforcement learning. So let's dive into it. If you remember from part 2, we finished that part by asking 3 different questions about different types of machine learning algorithm. The first question was, in which type of machine learning algorithm both the inputs and outputs are given? Basically, this is the supervised machine learning, supervised. In supervised machine learning, both the inputs and the outputs are given. In other terms, the data is labeled, and the machine is expected to detect some meaningful patterns or relationship from the data. Okay, so it means that the machine needs to make predictions. It needs to predict a class or a value, right? So the outcome of this algorithm is going to be a learned pattern. Now let me give you a very simple example to make sure that you all understand what's the definition of the supervised algorithm. Imagine you want to ask your toddler to help you cleaning his messy playroom, right? There are toys all around the place that the toys are in different types, different sizes, different colors. And you're going to say, okay, let's make 2 buckets and label them as a small and large. You don't let the toddler to start cleaning yet, right? You yourself will sort the toys based on their size, small and large, and then the toddler is going to just watch you at this step. After you sorted multiple toys, basically your toddler has been trained. Now it is time to test your toddler. Hopefully, he will put the small and large toys in their correct buckets. This is an example of supervised model, and the inputs are toys and the outputs are 2 labeled buckets. And your toddler is observing the outputs, right? So he knows that, okay, this toy is small, this toy is large, and etc. All right, now let's talk about unsupervised. The second question that we dealt with last time is, in which type of the algorithm only the inputs are given to the machine, and the machines are expected to detect some patterns, not necessarily the meaningful ones, by looking at the data, right? So in this algorithm, only the inputs are given, and there is no output. Well, or the output basically are not labeled. There's no output there. And the algorithm is expected to, again, learn some patterns, but the difference here is that the patterns are not necessarily meaningful, right? Now let's go back to our example. Same you, same toddler, same situation, and same messy room. Now, you just stand aside without doing anything, but ask the toddler to start cleaning the room or sorting the toys. You basically let him decide what to do, right? He may end up coming up with different sorting patterns, maybe using different buckets based on the toy size, colors, or types, or even based on something that you never expected. For example, a bucket for the toys with wheels and a bucket for toys without wheels, right? So why should you ever do that? Because the toddler may come up with some other patterns in the data that you were completely ignorant of, right? So this is an example of unsupervised learning, where only the inputs are given, and the toddler, the machine, is supposed to find the patterns in the data. Okay, now that we know what is supervised and what is unsupervised, let's talk about the third type, which is reinforcement learning. Reinforcement learning. So in this type of algorithm, both the inputs and outputs are given. Well, this is a little tricky because we don't necessarily call them inputs or outputs. There's an agent in this algorithm that it's going to explore and exploit the environment based on some predefined states and actions, right? And then it's going to get feedback from the environment, and based on those feedback, it's going to come up with the optimal policy, with the optimal path through some tries and errors. And now, if you want some real-world examples in our day-to-day living, I can say, oh boy, the kids are all about reinforcement learning. When they start to walk or talk, or even when they want to eat something, they're constantly receiving feedback from the environment and learn the right way of doing things by try and error. So this is the very simple example of the reinforcement type of learning. Now let's move on to the formal definition of all these algorithms. Okay, starting with supervised learning, what kind of models we have and what are the examples? In supervised learning, computers learn to model relationship based on trained data. This is important. And the inputs and outputs, as already we discussed, are labeled for the algorithm. After learning the pattern, the trained algorithms are used to predict outcomes for the test data. Okay, so what are the models? We're dealing with regression models and classification models. Regression models are the ones that the target variable, your left-hand side variable, are continuous, right? So y is continuous. And the classification models are the one that your y variable, your target variable, is the categorical, okay? Now let's look at a bunch of examples. So for example, for regression, you can think of, these are mostly econ and finance examples, but you can extend it to any kind of field, right? Imagine you want to predict stock market returns, right? The stock market returns, so because return is continuous, it's an example of regression analysis, right? And you can think of many features out there, right? I think in part 2, we talked about this Apple stock market pricing and look at a bunch of those features, right? So for example, the fundamental analysis, we had some technical indicators, we had some financial ratios, and more advanced, image processing and etc. Right? Those are all the features. Another example is that, for example, you want to predict the housing prices. Again, prices are continuous, so this is an example of regression, and you can think of many interesting features out there that have something to do with making predictions for the home prices, right? Then, another set of models are basically the classifications, right? Let's look at some examples. Imagine you want to generate buy, sell, or hold signals, in the stock market. So your target variable here can take 3 values, right? So you can even label them in whatever case you want. You can call it, for example, 1, -1, 0, or buy, sell, hold, and etc. Right? So this is one example. Another example will be estimating the likelihood of a successful M&A or IPO or SPAC in financial market, right? So you have a bunch of features, and at the end of the day, you want to predict that, you want to calculate the likelihood, or basically say that if it's going to be a failure or success, right? Third example, you can think of predicting credit default rate, right? It has huge applications in finance and insurance business, and basically you want to predict what's the probability of someone defaulting, right? And finally, you can think of classifying the funds or ETFs based on if they are winning ones or losing ones, right? So these are some the finance related examples, but again, as I said, you can easily extend it to any kind of other fields. Okay, so now let's talk about the unsupervised learning, what kind of models we have and what are the examples, right? So in unsupervised learning, computers are trained on unlabeled data, as we talked about it earlier, without any specific guidance. The goal is to discover the underlying pattern and find groups of samples that behave similarly. Well, the objective is a little tricky. It's a little fuzzy in unsupervised because basically you don't know what you're looking for, right? It's difficult to know how well you're doing. You're trying to find groups of samples that behave similarly or find a linear combination of features with most variations, right? So what are the types of unsupervised learning? We can have clustering and principal dimensionality reduction, right? So in clustering, basically you can use clustering algorithm on your data set, and at the end of the day, maybe unexpected things can suddenly pop up, right? So let's look at a bunch of examples in finance. In finance, we usually group the companies based on their sectors or countries, right? But what if you want to make that grouping, basically you want to make those companies into peer groups based on some non-standard characteristics, like financial statement data or corporate characteristic, right? Remember, we don't necessarily know what we're looking for, right? And we hope that maybe some pattern pop up that we didn't completely expect, right? So this is one example. Another example is that, for example, you are doing client profiling and asset allocation, right? Traditionally, how do we do asset allocation? We look at their income, time horizon, and more importantly, risk profile to just provide them with some consulting in terms of asset allocation. But what if we want to come up with some other patterns in the data? We want to profile the clients based on some other characteristic that we are not aware of, right? So this is another application of clustering in finance. And then finally, we can do portfolio diversification and stock selection based on co-movement similarities. Instead of looking at different sectors in stock market, we want to say that, okay, maybe these companies had we want to put them in the same group because they have co-movements, right? We can look at their correlation in their returns, right? So for example, here's another example. We know that Ford, GM maybe are in the same industry, Apple, Facebook, Google, again in the same industry, and Goldman Sachs, JP Morgan, and UBS are in the banking industry, right? But what if, at the end of the day, if you look at their co-movement similarities, maybe Goldman Sachs and Apple's are behaving very similarly. So why put them in different buckets? Well, maybe we should put them in the same bucket. Okay. So these were the examples of clustering. Another type of unsupervised learning method that we use is called dimensionality reduction, right? And we usually use dimensionality reduction as the name suggests, to reduce the dimension of the data set, right? So sometimes, especially in finance, when you want to come up with some features in order to predict the stock market return, there are hundreds of them, and if not exaggerating, thousands of features out there, right? And we know that necessarily not all of those thousands are useful, or maybe many of them are very highly correlated. So how can we reduce the dimensionality of the data? So this is another technique that we use. We call it dimensionality reduction, and it's a type of unsupervised learning. So an example is we want to identify the most predictive factors underlying asset price movements, right? So this is basically to avoid what we call factor zoo in factor modeling asset pricing. Okay. So in general, unsupervised learning methods are different from supervised learnings, but can be useful as a pre-processing step for the supervised learning models. Okay, imagine you want to reduce the dimensionality of the data and then on top of that apply a supervised learning model. So it can be a combination of the two. Now, finally, let's talk about reinforcement learning. In reinforcement learning, a computer, or the agent, learns from interacting with the environment, right? By producing actions and discovering rewards. Remember, you need to define the environment and actions and the reward system. The machine will then explore and exploit to maximize the reward. The new actions may not be immediately optimal. It means that there might be a delay between actions and reward, but the learning happens basically through millions of trials and errors at the end of the day. Okay, so let me give an example of reinforcement learning in finance. So imagine you're talking about a virtual trader, right? At the end of the day, you want to design an agent that's going to trade on its own, right? So the virtual trader, the bot, is going to be our agent here. The agent is going to follow certain trading rules. These are the actions that are predefined, so we can say, okay, buy, sell, hold, and etc. So in this example, we have basically two actions, buy and sell. And the agent does it in a specific market, and that market is our environment, right? To maximize its profit. The profit is going to be the reward system, right? And it's, again, depending on the period of the, for example, based on the trading period, is it minute based, hourly based, or daily? There can be a delay. There can be a significant delay between action and reward, right? But at the end of the day, the agent should be able to optimize itself by going over thousands of iterations and hopefully come up with the algorithm. So for example, says that, okay, buy here, maybe sell here, buy here, sell here, buy here, sell here, and etc.
All right, the next natural question that you might ask is what kind of machine learning models do we cover in this course, right? So here is a roadmap, and I'll be talking about supervised and unsupervised in this course. This is an introductory course, and then in more advanced courses like the deep learning one that we offer, we are going to talk about reinforcement learning, semi-supervised, or even self-supervised models, right? But for this one, as an introductory course, we will be covering these ones. So for supervised, we deal with regression and classification, and these are the models that we cover. And for unsupervised, we will be talking about the methods for reducing dimensionality of the data. Basically, we will be talking about principal component analysis, and we will cover a couple of clustering techniques like k-means and hierarchical. Okay, this concludes our module number 1, Introduction to Machine Learning. Hopefully you have a good understanding of what it is, what's the definition, and what is the difference between machine learning, deep learning, AI, econometrics, and how do we use them in real world for different applications. In the next module, we will be talking about how to set up your Python environment, and for module number 3, we will get into the details of all these models that we cover. Before you leave, I want to remind you of a warning that applies to any kind of machine learning algorithm that you're using, especially if you're dealing with structured data, tabular data, a data set that has some simple rows and columns like an Excel spreadsheet. So remember, a machine learning algorithm will always find a pattern, even if there is none. So what does that mean? It means that you can make these models a lot more complex in a way that it can find something that it's not there. This is basically some noise, and it's remembering those patterns. And this is not necessarily a good machine learning model. A good model, as we talked about it briefly, is a model that is generalizable. So it means that it is flexible enough to find the patterns in the train set and apply those patterns that are existent in the test set as well. So we're going to talk about all these details in the future module, but I just wanted you to remember that so here's the saying, if you torture the data long enough, it will confess. So while we are going over, different machine learning algorithms and how we can make them complex and flexible, just keep in mind that sometimes, especially for structured data, the goal is not to necessarily come with the most complex model. The goal is to simply find a model that can perform best in the data set that it has not seen before. All right, until the next module, take care.